Modern data engineering teams are offloading code generation to AI agents, but that workflow hits a hard limit when touching a real-world enterprise system. The raw size of the codebase heavily exceeds the agent's capacity to maintain functional reasoning. Take Claude 4.6 Opus. It boasts a 200,000 token context window. That sounds massive, but feed it an active data platform alongside internal READMEs, API documentation, and legacy architectural notes, and that window fills up immediately. As the agent executes commands, recent terminal outputs flood into its active memory. To process the new output, the model must drop older information from the window. It drops your architectural constraints. This process is called context decay. The consequences manifest immediately. The agent hallucinates API parameters. It invents fake function signatures. Instead of accelerating development, engineers spend hours debugging phantom functions the AI confidently wrote from scratch. This chart shows the token consumption and associated cost of the brute force approach. Pushing full documentation into the prompt requires 50 to 100,000 tokens per interaction. For a data engineer running multi-step workflows, this burns through an API budget in hours. Context decay is a massive structural flaw. Asking a single tool to simultaneously store vast amounts of documentation and execute precise code changes ensures it fails at both. To resolve this, we must physically decouple the execution memory from the institutional memory. To build this, we look to Google's NotebookLM. While often framed as a consumer study aid used to summarize PDFs, its architecture suggests a more powerful application for engineering. NotebookLM functions as a static, holistic, retrieval-augmented generation, or RAG, engine. RAG is a framework that retrieves facts from an external database to ground the generation of AI responses. This specific engine operates on Gemini's 1 million token context window. By combining these systems, we establish a strict division of labor. Claude 4.6 handles execution exclusively. NotebookLM serves as the permanent, holistic knowledge base. This decoupling forms a workflow grounded in verified sources. To build it, we construct a 3-stage federated intelligence architecture. Stage 1 standardizes the raw inputs from a sprawling legacy codebase. We use a command line utility called repomix. Repomix is designed to ingest an entire data platform repository in one pass. It filters the system, stripping out lock files, binaries, and compiled build artifacts. The output is a single tokenized markdown file. It contains the logic and structure of your codebase, without the execution bloat. Without this distillation, a knowledge engine chokes on useless metadata. With it, the AI maps the structural architecture accurately. Stage 2 uses this tokenized markdown to construct the knowledge base inside NotebookLM. This includes authoritative API docs, practical code walkthrough transcripts, and contextual internal READMEs. These explain why architectural choices were made. Standard RAG implementations process this amount of text using vector search chunking. They slice documents into smaller mathematical pieces to search for keywords. This diagram shows the problem with chunking codebases. Slicing interdependent logic across separate geometric chunks severs a dependent variable from its declaration, creating critical retrieval gaps. NotebookLM uses holistic ingestion, processing the entire 1 million token graph simultaneously. Architectural links remain unbroken. Because it reads all sources holistically, the system behaves differently when queried. If a piece of data is missing, it refuses to answer, rather than guessing to fill the gap. By replacing vector chunking with holistic RAG, the system eliminates the primary cause of hallucinated API parameters. Stage 3 builds the automated bridge between Claude and NotebookLM. A utility called the NotebookLM skill utilizes Playwright, a framework for reliable browser automation, to let Claude chat directly with your NotebookLM interface. This skill forces the agent to follow a strict 4-step stateless protocol. It opens the browser, asks a question, retrieves a cited answer, and closes the session. The token economics drop dramatically. A stateless lookup costs approximately 3,000 tokens. Compare that to the 100,000 tokens required to inject raw context directly into the prompt. Because the session closes after every query, Claude's context window remains completely clean. That space is reserved exclusively for logical reasoning. The stateless bridge provides access to the full knowledge base with zero context bloat. We can apply this system to recover an undocumented legacy ETL pipeline. ETL stands for Extract, Transform, Load, the standard process for moving data between systems. The engineer starts by commanding NotebookLM to generate a 1 to 2 page engineering brief that maps out the system architecture and identifies execution risks. This engineering brief is then pasted directly into the Claude.md file, which sits at the root directory of the project. The engineer initiates Claude with a precise directive: follow the engineering brief in Claude.md. If unsure about API parameters, autonomously query the NotebookLM skill. The Claude.md brief provides the initial orientation, while NotebookLM resolves specific technical queries on demand. This removes the manual research overhead from the development flow. Claude 4.6 introduces a multi-agent capability that further optimizes this workflow. You assign a lightweight researcher agent using the Haiku 4.5 model to handle the NotebookLM queries. The primary builder agent on Opus 4.5 focuses entirely on implementation. The smaller node continuously loops with the database, feeding verified, cited information to the builder in parallel. This workflow has constraints. Opening browser sessions through Playwright introduces latency. Each query takes anywhere from several seconds to a full minute to process. The ingestion process is static. When the agent successfully updates the code, those changes are not automatically reflected in the notebook. Repomex must be manually rerun to update the knowledge base. Uploading proprietary legacy codebases to Google's infrastructure raises privacy and compliance concerns that require strict scrutiny from enterprise security teams. For data engineers, the manual copy-paste between browser and terminal ends. It collapses into a unified flow, commanding specialized tools that collaborate behind the scenes. Teams that adopt this federated approach preserve cognitive energy for high-level system design. They leave the rote lookup and citation-backed execution to the agents.